In this video, we're looking at 2021 Paper 1, Question 7. Here we're dealing with sequences and series. There's a pendulum and the arc length of its first swing is 45 centimeters. Every preceding arc length is 90% of the previous one. So the first part is very straightforward. The first one was 45 centimeters, the next one was 90% of that. So you get 45 and you multiply by 0.9 and you get this. Multiply by 0.9 again and again and again, and you get the arc length of the first 5 swings. Obviously here we're talking about a geometric pattern here, because in this case there's a common ratio. The common ratio is 0.9 and the first term is 45. So that's what we're going to use to answer a lot of the first part of this question. In part II, we're actually told the general formula. Remember, the general formula from your maths tables is a times or to the power of n minus 1. They've just subbed in the a is 45 and the or is 0.9. We're asked to use this to find the length of the 25th swing to one decimal place. So we simply sub in n equals 25. Plug it into your calculator and you should work out that the 25th swing, the arc length of it is 3.6 centimeters. In part 3, we're looking for the total distance travelled by the tip of the pendulum after 40 swings. We know the first swing, the tip of the pendulum travels 45 centimeters, then 81 over 2 and so on. We've identified already that it follows a geometric pattern, where a, the first term, is 45, or the common ratio is 0.9. I want to work out, if I added up the first 40 distances, what would they all add up to? Now you could use Tn, you could get T1, T2, T3, you could add them all up. But obviously it's far more efficient here to use the formula for Sn. So since we're using Sn, we just need to sub in our A, or, and N. Plug it all into our calculator and we identify that after 40 swings, to the nearest centimeter, the tip of the pendulum has travelled 443 centimeters. Okay, in part 4, we're asked to identify what is the first swing whose length is less than 2 centimeters. So there's a couple of different ways of doing this. Like, if you wanted to do it the wrong way, shall we say, is you could go back to part I and you could just keep on multiplying by 0.9. We already have the length of the first 5 swings. If you just kept multiplying by 0.9 again and again and again, eventually one of them would be less than 2. That's the one you're looking for. So maybe it's the 50th one, or maybe it's the 60th one, or whatever. But that's certainly not the way that you should be trying to approach it. Let's think about this in terms of the formula. I want to work out what is the first term that's less than 2. From part II, we know the general formula for this pattern is 45 times 0.9 to the power of n minus 1. And I want to know what is the first one that is less than 2. Now you could actually solve this and you'd end up with your answer. I find, and the way that I tend to always teach students is, I think you're better off to try and solve it for when it's equal to 2. I want to work out after how many terms will it be equal to 2. Chances are my answer won't be a whole number, but if it's not a whole number, I can go back and I'll figure out whether I should round up or round down. So we'll address that in a moment, why I'm using an equals rather than an inequality, but I think it's easier to deal with if you try and find the value of n for which the length the pendulum will travel is equal to 2. Here we have one equation and one unknown, so we can solve for n. The first thing I notice here is that the unknown is in the power, so I'm going to have to introduce logs at some point. However, I can't introduce logs yet because I have to isolate this first. So the first thing I'll do is divide both sides by 45. I'll get 0.9 to the power of n minus 1 equals 2 divided by 45. Now that I've isolated the part of the expression with the unknown in the power, I'll introduce logs. If we introduce the natural log on both sides, it's probably the easiest way to go about it. So I'm introducing, literally just putting in ln in front of the left hand side and ln in front of the right hand side. Now the third rule of logs on page 21 tells me that if I've log of something to a power, I can simply bring the power in front. So I'm simply going to move the n minus 1 in front. I have n minus 1 times ln 0.9, and that's equal to ln 2 over 45. So notice here the problem was the unknown is in the power. Solve the problem because there's no more powers. The unknown is now, it's no longer in the power. So that's the point of what we just did. Now, what I might do next is try and isolate the n minus 1. So what I'm going to do is I'm going to divide both sides by ln 0.9. And I end up with ln 2 divided by 45. And it's ln of all of that, so I have to be careful with my brackets there, divided by ln 0.9. Next, I'm going to plug that into my calculator, and I'm going to be able to work out a value for n minus 1. Then obviously it'll be easy enough to work out a value for n. So I plugged all of this into my calculator and got 29.55. So n minus 1 equals 29.55, so I add 1 to both sides. That means that n must be equal to 30.55. Now we have to consider, the answer is either 30 or 31 here. I have to figure out, should I round up or should I round down? So let's think about the actual question here. The question started off, well, the first length that the pendulum travelled was 45 centimetres. The next one was 81 over 2. Gets smaller and smaller and smaller and smaller. I know that if I continued this on, the 30.55, that would be the first term. That term is equal to 2. What that obviously means is before the 30th term, it's greater than 2. It's 45, then it's smaller and smaller, but it's still greater than 2. If I was to take term number 30, that one would be a bigger number than 2. It would be 2 point something. But then the 30.55, the 30.5th term is equal to 2. Now obviously that doesn't really make sense. What it tells me is the term 31 is the first term that's smaller. It's 1.9, or it's smaller than 2. So the 30th term, I'm not quite there yet. But by the time I get to the 31st term, I've crossed that threshold. The 31st term, that's the first one that's less than 2. So your answer in this case, it's term 31, and in the context of the question, P must be equal to 31. Okay, so now we're turning our attention to part B. In part B, we're starting to consider the angle at the center. So think about your pendulum. It travels 45 centimeters in one direction, then it travels a little bit shorter on the way back, a little bit shorter, a little bit shorter. So the angle, the arc length in each case is getting smaller and smaller and smaller. The other thing that's getting smaller is the angle at the center. Obviously what happens with each swing is that it doesn't swing out as far. It swings out a little bit less each time. So the angle at the center is also a geometric series. It's also 90% of the previous angle each time. Now for part I, B part I, we're just considering the first swing. We're told that we know the arc length of the first swing is 45 centimeters. And the radius, or the length of the pendulum is 1 meter. Notice one of them is in centimeters, one of them is in meters. So you have to either convert them both to centimeters or both to meters. And it really doesn't matter which one you do. In this case, I decided to write them both as meters. The radius of this arc is 1 meter, and the length of the arc is 0.45 meters. So I took my 45 centimeters, divided it by 100. If you go to page 9 in your maths tables, you get this formula. A formula with the arc length, the radius, and the angle at the center. Obviously what we want, because we know the radius and we know the arc length, so we can find theta. So all we do is sub in. Our L is 0.45, our radius is 1, the only thing we don't know is theta. What I decided to do then was to get rid of the fraction on the right hand side, so I multiplied everything by 360. Then what I decided to do next was divide both sides by 2 pi to get theta on its own. So theta is simply 0.45 by 360 divided by 2 pi. If you plug that into your calculator, theta works out as 26 degrees. Now in B part 2, we're asked to work out the total accumulated angle that the pendulum swings through when it stops. Now it's important we look back at what it said at the start of the question. There's no mention of this pendulum ever stopping. The pendulum originally it swings 45 centimeters, then 90% of that, then 90% of that, then 90% of that, and so on and so forth. So in theory, the pendulum never stops. Because if you keep multiplying by 90%, if you keep multiplying by 0.9, the number gets smaller and smaller and smaller, but it never actually reaches 0. Now you know yourself, like practically, if the number gets small enough, the pendulum is basically, you won't be able to see the pendulum moving, but in theory, the pendulum never stops. So actually, it's asking me to add up the angle in the first swing, the angle in the second swing, the angle in the third swing, and so on. But you have to realize that theoretically the pendulum never stops. The swing is just 90% smaller. It gets 10% smaller each time. It's 90% of the previous one. But theoretically, it doesn't stop. It's going to keep going forever. So they're asking you to get S infinity, the sum of the first one and the second one and the third one. After a while, the number gets so small, the angle that it swings is so small that it might as well be zero. And when we were learning about S infinity, that's the way that we thought about it. So we're talking about the angle here. And in part I, we worked out that A, the first term in the geometric series for the angle, the first one is 26 degrees. And I know that the arc length is 0.9 each time. So the angle obviously is equivalent to that. The angle 0.9 at 26 will tell me what the angle is in the second one. 0.9 of that will tell me what the angle is for the third one. So it's a geometric series where I have my A and I have my OR. And I want to know, if this goes on forever, if I add up all of the angles, what will it add up to? First of all, you definitely are allowed to use S infinity here because your common ratio is less than 1. Remember, if it's between 1 and -1, then you can get S infinity. So all you do, you plug in, it's 26 over 1 minus 0.9, and you work out that if this pendulum, if you allow this sequence to go on forever, the angles will add up to 260 degrees. Now in B part 3, we're asked to work out the total distance travelled by the tip of the pendulum when it has travelled through half of the total accumulated angle. Now there's a couple of different ways of doing this. It says hence or otherwise, and the way that I'm going about it is actually by the otherwise method rather than hence. I'm not actually going to use our answer from part 2, although it's relatively straightforward to do so. As we explored in part II, when they asked, we want to work out when it stops. When it stops, that refers to S infinity, because technically it never stops. It gets smaller and smaller and smaller to the point where it might as well have stopped. So I'm talking about the length the pendulum travels here. It's a geometric series. The first term is 45, the common ratio is 0.9. If I wanted to work out the total distance travelled by the pendulum, just like for part 2 we worked out the total angle travelled, this time I want the total distance travelled by the pendulum. It's A over 1 minus OR. Essentially it works out as 450 centimetres. That's the total distance travelled by this pendulum. But this part of the question asks me for half of the total. I want to know how far has it travelled when it's halfway towards infinity, or halfway as far as it's going to travel. So if S infinity is 450 centimetres, half of that is simply 225 centimetres. And that's your final answer for part 3.